Today we're going to talk about modeling process flow loops in GoldSim. I'll start with some simple models and discuss some concepts that will or may likely come up in these kinds of models. And some of them can be a little bit tricky, and so I want to start with very simple models, and I hope that after we see those, then looking at a more realistic, larger model, which is based on what you see here in the screen capture, that it might all come together at the end. And I've had, since announcing this, I've had some people ask about these custom icons that I used in this model, and so at the end, if we have time, I'll talk about how to add those, and then also show you where to get those if you want them, or how to create them yourself. I created all of these. Okay, so let me start with a very simple model here, and well, I shouldn't say very simple, but this is a model that you might be familiar with. I've discussed this probably a couple of times in the last year and a half in previous webinars, and it's been up on our library for quite some time. Those of you new to our library, you get there by going to our website, clicking on library, and you'll see there's a model library and an image library. Both I'll talk about today. But in our model library, it's categorized here. You can also search here. Anyway, that's where this this particular model comes from. But the reason it's up there is it's really important. These concepts come up a lot especially in water balance models, mine water management models, water resources, models that involve water, flowing water and storage and controls to discharge water from a pond or tank or reservoir, and also control flows going in to these things as well. So the reason I want to show you this one is because things get more and more tricky as your controls begin to require changes on more than, or on a frequency that's smaller than your time step. And so let me explain what I mean by that. This particular model that we're looking at here has time steps of 1 day. Let me go back to edit mode so you can see that a little bit better. Okay, we're in edit mode now. Going up here to the simulation settings, and we're looking at the basic step, calculation step. It says 1 day. Okay, so the control logic that we have in these containers represents little ponds where water is flowing in, and we have a pump that discharges water out of the pond, and we control when to turn that pump on and off based on a low water level. So I'll run the model and show you what I mean by that. I'll start with this if statement. The if statement is in here to represent what's called a discharge request. That's highlighted in yellow here. And what it says is, if I go to the if statement, it says if the this reservoir, or in this case it's called pool, is greater than 0, then go ahead and tell it that we want this water demand. If the pond is down at 0, if there's no water in there, then turn it off. Now it doesn't look at inflows at all. In theory, I guess you could say if there's any inflow and or water stored in the pond, then you can request water to come out. But I will say that this kind of logic we see a lot in people's models, and it can cause problems, especially when you have multiple storage elements in your model. And the reason for that is because GoldSim inserts a time step every time a reservoir or a pool, in this case a pool element, hits an upper or lower bound. This kind of logic would cause us to discharge water until we hit a lower bound in many cases, unless the inflow is greater than our demand. But for the most part, you're going to be hitting a bound often with this kind of logic. Okay, so if I look at the pool volume, what you see is that it appears that we're hovering just above 0 here as the reservoir draws down to a near 0 volume. And what we're looking at here is a temporary plot. So I just right-click on the pool and go time history. This is a temporary plot, which means that it does not show us any values at any inserted time steps. It only shows, if I go to the table, you'll see it shows us only the values at the basic steps of one day. But like I said, there could be things happening between time steps because we're hitting the lower bound. And so in your simulation settings, if you go here to the advanced, you'll see there's a checkbox that allows you to view unscheduled updates. These are times between the basic steps. If any are inserted, it will show you results at those as well. This would be a temporary selection that you should make. I wouldn't recommend doing this all the time, but just to check your model. Okay, so if you have a time history element already created, then what you'll see is if you have the option to view high resolution results, you'll see in the display over here it says high res, meaning that high resolution results are saved in this chart. And so now when we look at the this chart and we go to the table view, you can see that indeed it is showing us points in which the we're between the time step of one day. If I scroll down, you'll see we hit some here where we're hitting the lower bound of this particular reservoir, and it causes us to insert a step right at that point. And then the water fills up a little bit, and then our water supply, as you can see, the pumping amount over here is oscillating between 1 and 0 over there. Okay, so that's where the oscillation is coming from. It's as soon as we start to draw down to the lower bound, and we have to begin to shut the flows on and off, which looks like this. Okay, so another option to control flows from a reservoir, and I don't want to go into a lot of detail on this because this is, like I said, a previous webinar I've given, and it's not really the point of today's webinar, but it's important that you see this because it makes a difference in models that have smaller volumes in the storage elements, which is what we're going to be talking about. Okay, so another option is to use a lookup table that will essentially apply a factor to a request to slowly reduce it over time. And what you get is something like this, where instead of shutting it on, off, it just ramps it down. And so the red line is the water supply. As you see, the volume in the pool begins to draw down as it gets to a lower level. Then we just draw down the water supply slowly, and it kind of prevents that oscillation that you see. Okay, so that's another option. And then finally, the reservoir status element, which in a lot of cases are probably the best way to go, because this operates truly in the way that a real system would be operated. And this is where you have a status element that is told to turn on or off and then remains in that state until it's told to turn back the other way. And this prevents the oscillations that you see in the if statement. So this is a much better way to do this kind of control over the if statement option, which we saw at the beginning. And so here you see that the reservoir, and I need to add the reservoir. Looks like it got turned off somehow. Okay, so when the reservoir level draws down to some point, we shut the pumps off and we keep them there. Even though the reservoir is rising, we just keep them there until we say, okay, the reservoir has come up enough, now let's turn it back on. So it prevents some of that oscillations. Okay, so all of these options are great, and they work especially well when your residence time in your storage element is large. Well, in particular, larger than your time step. Okay, but what happens if your storage elements are small? And this is a case that you run into when you're simulating a lot of times process flows in a system where you have, relatively smaller tanks. These the water in the tank might turn over because of the high flows in less than a time step. And so let's see what happens when you get into that kind of a situation. So I'm opening up the same exact model. I took out some of the details, but it's the same model. And what I did is I made the volumes much smaller. Before we were talking megaliters here, now we're talking cubic meters and a much smaller amount. I changed the stage area relationship a little bit too to be smaller. Okay, so now we run this model, and I'm going to change it. I was playing around with the time step here, but let me change it back to 1 day because that's what we had before. And now run the model, and now we go into one of these, looking at the same thing. And what you see here is that, well, because the volume in the storage element is so small that it fills very quickly, right? It fills in less than a day. And then when we ask for water to be removed from it, it's the flow is high enough that it can be withdrawn in less than a day. And so you see a lot of oscillation going on here. If I zoom in, then you can see, right, it's a lot, all within a period of less than a day. The reason we are seeing so many inserted time steps between the days is because of reservoirs hitting lower bounds in this case. Actually, in all three of these cases, the reservoir is hitting lower bounds. I don't know about the status. Let's look at this one. Yeah, I don't think the reservoir in this case is. Hang on. Let me add the. I don't know why that was turned off. Okay, so I don't think we're hitting the lower bound on this in this case, even though it might look like it. Maybe we are. Oh, we are. Yeah. Okay, and there's just not enough water in the storage element, right? It's so small. And so what you can do in a model is, if you're wondering if you're in this kind of a situation, you can always calculate the residence time in the storage element. So here's a simple calculation here, residence time, and I just said what's the amount of water in the pool divided by the outflow. I suppose you could say inflow too, but anyway, you'll get a good idea here when you look at the plot, where it's showing us that we are less than an hour, in fact, on our residence time. So that means you're going to have problems with sub time step oscillations, definitely, with this kind of logic in this model. So one thing you could do is say, well, I mean, our residence time is so small, it's sub-hourly, we should just have smaller time steps. And so we could do that. We could say, well, let's just make it be 0.1 hours on our time steps and run the model. And now what you see is, okay, now we don't have as bad of oscillations. You see there's a little bit right over here, but you can see that it looks much better, right? And the reason for that is because we are updating calculations on such a small time step that we're able to not overcompensate when we say, okay, withdraw some amount. It will only do it for a short amount of time. Therefore, it's not that, it's not as much water going in over the time step, right? Because it's a small time step. So this is one way to deal with it. But I'd have to say that this can be very expensive, right, in a big project model, because maybe it already takes you 10 or 20 minutes to run the model. Now changing your time step by increasing it by this much would make it that much longer. So sometimes this is not an option. One thing you can do, however, if you decide to go that route of making it have a smaller time step, is, and you don't want to show it, you don't want to show results every 0.1 hours, you could use reporting steps on a daily basis. So you could say, I want reporting steps of 1 day, and only save results for the reporting steps. Then when you look at a chart, you can change the simulation time type chart to a reporting period type chart, and then just say, I want to look at the average. So there might be a whole bunch of stuff going on between the time steps. You don't really care, and it could be true. It could be that in reality, pumps are actually being turned on and off every, I don't know, half hour or something. But because you need to only simulate for a daily time step, then you could do it this way with reporting periods. And then when you run the model, then it will report just average flows, right? So then you don't see all of the oscillations going on, even though they're actually happening in the model. So that is an option there. Okay. So with that, I just want to show another model. Let's save that. Okay, here's a model that calculates discharge from a pond using a hydraulic calculation. I don't know why, let's see. And in this kind of situation, you often hit the same kind of issue where anyway, you often hit the same kind of thing where because of the limitations of the hydraulic calculation, when you get into situations where it doesn't apply, you start to overcompensate potentially and calculate something that is too high for what it can for what can represent a reality here. And in this case, what we have is an orifice calculation. So here's a picture showing what's happening. We have a reservoir here with an orifice at the bottom of the dam, and as the water level is changing, then the flow coming through this pipe also changes, and it uses the friction losses in this pipe and calculates the difference in energy between the point in the reservoir and the discharge point using Bernoulli's equation. But the important thing here is that it's looking at the orifice and the friction in this pipe to calculate the flows. That actually requires an iterative calculation to solve for that, so there's a script element being used here to calculate that. I think you can also get this on our library. But anyway, it uses just a binary search algorithm to calculate that. We don't need to worry about that too much. The point is that when the water level gets too low or it gets down to the area, the zone of the pipe, then the flows are going to be, the flows that it calculates are actually higher than what is real for this particular equation that I have, which is for assuming a full pipe discharge here. So obviously it gets more complicated when you get to a non-full pipe down here at the bottom. In addition to that, you also get into a situation where the amount of water in the pool when the water level's low is so low that any amount of discharge that you calculate is going to be greater than that volume. So in other words, your residence time is dropping, going very low, smaller than your one-day time step. Okay, so if I run this model, what we see, if we look at a plot here, what we see here, and in fact, what I want to do is just do a regular run without showing you inserted steps, because this is what what happens to a lot of people. Okay, so I just went to the simulation settings and I turned off the option to include high resolution results. Okay, so I run this model and we look at this chart, and it doesn't look that crazy. It's just showing us that we have some water in this pond that rises up here, and then it draws down, and it's kind of jumping up and down. If I zoom in here, you'll see that it's kind of jumping up and down, but it doesn't look too bad. It does show that our discharge flow is up here in the green, and the reservoir volume is down here. So every time the reservoir volume rises, then our discharge tends to rise as well. This is not the full story. What is actually happening. Okay, this is what happens at the one-day time steps. And if I zoom in, you'll see that we are on one-day time steps. So March 7, okay, this is every 2 days, but anyway, you can see that we only have changes every 1 day. So this is showing us exactly what happens at midnight on each of those days. But it turns out, because our flow is so high and our residence time is so low, if I plot that, you'll see our residence time is often down here below 1 day, even though our calculation basic step is 1 day, right? So we have a residence time that's below that. All right, so if I do show high resolution results and plot this again, then what you see is more oscillation. So let me zoom in here. So what you're seeing here is that the reservoir, well, let me zoom in a little more. Okay, so the reservoir is filling, and we're discharging, and then we get to a point where we discharge right here. We say we calculate a discharge amount because there's water in there, and it says, okay, that is going to be, a discharge rate of this amount, which drains the pond, hits the lower bound, inserts the time step, and so we have time steps that are occurring sub-days here, and it's causing some oscillations. Okay, so this can be an issue if you don't know that it's happening, right? So make sure when you're running your model that you, if you're approaching a lower bound or an upper bound in that case, make sure you go here to the simulation settings, advanced, and say include unscheduled updates. But another thing that will give you a clue if you have this kind of issue is to just look at your residence time in your pond. You have a small amount of water compared to the flows that are coming in and out? And if so, you should look at that. Something that you'd probably want to do in this discharge request is have a reduced discharge request as you approach the lower bound. What I would typically do is I would say, okay, if the water level's up, high enough and it's not an issue, then use that equation. But as you begin to approach that point where your time step is greater than your residence time, then I would put in a different equation. So, for example, you could say use a min function that says min of this discharge request or the amount of water that's stored in that little pool at the very bottom divided by your 1 day or something like that, just as you approach the bottom. And then that way it would say, okay, we're going to disregard our hydraulics once we get to that point of a low pool, and we'll just do kind of more of like a mass balance type of average daily flow in that case. Okay, one more concept I want to show you is a looping flow. All of these kind of things come up when you're dealing with these kinds of process type models. Okay, so here's a model that has a loop, a flow loop, and I've labeled the nodes in this loop Q1, 2, 3, 4. Q1, 2, 3, 4. And in this case, it's just a simple flow loop, and it's just saying, okay, we have some water that's flowing around in a circle, and at some point there's some losses occurring off of this loop, which is right here, just using a splitter. It's just really simple. It just says 20% of whatever comes in is then lost here, and the remainder goes into Q4, which is just the balance of the splitter. That's the balance output, right? So the splitter has two outputs, a loss and the balance. Those are defined here. I guess you could call that whatever you want. You could call it, well, anyway, that's the remaining amount of water that's in the flow loop. So that comes back around, comes over to here, and then we have some makeup. It's making up for whatever is lost, and then that comes back into the loop. Obviously, this is circular in reference here, and so therefore we put in what's called a previous value element. You could also put in a delay element. Now, in a lot of models, we've been recommending that you use a delay element instead of a previous value. And there are reasons for that. If you truly do have a delay in your flow system, then you should use a delay element and not a previous value. I'm using a previous value in this case for a very specific purpose. But in your models, if you truly do have a short delay in your flows, and you do need it to break the recursive loop, then I would use a delay, and I would use a material delay actually. So the material delay looks like this. And so I could use a material delay instead of this previous value element. Anyway, the previous value element, all it does is refer to the value that was previously calculated, obviously, like it has it in its name. Okay, so when we run this model, what I want to show you is the comparison of Q2 and Q3. The only thing that's happened between these two nodes is that we've put in a previous value in between it. So I run this model, and I plot Q2, and I add to that Q3, And what you see here is a one-time step delay, right? Because it's referring to its previous update. And sometimes this is a problem. Not all the time. A lot of times this is fine, right? Because it's close enough. You have other, maybe you have other uncertainties in your model that are much greater than just having a simple one-time step delay. But in some models, it is a big deal. Some models have larger time steps, like 1 month, and you can't afford to delay things by a whole month. But in a lot of cases, you're looking at a real, like a process flow model, and in reality, that's not what you have. You actually don't have a delay of 1 day, 1 whole day in your flow model. And so if it is an issue, then there is a way to get around this, and it's a little bit tricky, and that's why I wanted to have this webinar. Okay, so right now we're seeing, yeah, there is this, this 1 day delay in here. And I did mention to you already that this previous value element, the way that it works is it takes whatever input you give it, which in this case is Q2, and it says, I'm going to report on the output side whatever was previously updated. And right now it's looking at the value on the previous time step, the previously calculated or updated time point in the model. And if there are inserted time steps, it will take the value of the previously inserted time step. So it's not always a delay of a whole day here that you might see. Okay, so that's an important point to make. If you have inserted time steps happening, like let's say, for example, that you had an inserted time step that happened 5 minutes ago, then the value that's reported on this element is going to be the value 5 minutes ago of the Q2. Okay, so that's another reason why some people want to use a material delay, because you can specify that, no, I want an exactly this amount of delay. I want 1 day delay or a 5 day delay. I don't want it to ever be shorter than that. And the previous value element, that's all it does is it picks up whatever was calculated in the last update. And it could be 5 seconds ago, for example. All right, but one thing we can do with this flow model, and I guess I should show you some results here. Let's see. So the loss rate, it looks like this. You can see liters per second. It's peaking at 7 liters per second. The flow at Q4 is approaching 30 liters per second. And the way that we calculate the makeup flow that comes back into the loop is we just say, well, we know what the target flow needs to be in this loop. So subtract whatever's coming back around recycling, which is Q4. Subtract that. That's our makeup flow that needs to come back in. Okay, so that means that Q4 should be the same as the target flow. So let's just check that. And you can see that it's not exact. And you can see it's delayed. There's some delay there on that peak, and that's because of this delay element, or this previous value element that we have. Okay, so one thing you can do is you can cause your previous value element to refer to not the previous time point, but the previous loop update. And so what we can do is we can go to our container. So I just came out. Let me show you the browser view. So we were just inside of here, inside of this container called flow circuit delay. You can see it up here as well. So if I go up a level, you'll see we were in this yellow container here called flow circuit delay. What I can do here is I can change this container to have a looping capability. And it's not anything complex. All I'm going to do is say I want to loop until the loop count, which is an internal property within this looping container, only if it's a looping container, by the way. I want to loop until the loop count is greater than, let's just say 3. So not that many loops, but what it means is every single time step, the calculations inside of this looping container will update 3 times. Okay, so if I come in here and we run the model again, and if I compare Q2 to Q3, then what you see is they are on top of each other. And the way that this works is it says, okay, on the very first loop of this looping container, this previous value element will access the previous time point, just like it was doing before. But then we update the calculations a second time. And on the second calculation, the previous value element says, I'm going to capture the value that was calculated on the previous loop value. It's just whatever was updated last time, in this case the previous loop. And so it's no longer looking at the previous time, it's now looking at the previous loop. And depending on the complexity of your system, you will be able to remove any kind of delay that you're seeing with the previous value element. Now, there are some cases where you have a lot of coupled flow loops, and this simple solution may not work. And so I'll show you another workaround to get around that. But I would say a lot of cases this is fine, and it should work in just a simple or just a single loop like this should be just fine. Okay, so then if we look at the target flow compared to Q4, you can see that it's much closer, right? We don't have that delay there anymore. Okay, and the reason it was a little bit less is because our makeup flows are making up for what it sees here, but then it's immediately lost afterwards. So, okay, there's another way we can do that, and that is with looping that uses a solver to loop. So instead of just specifying a constant number of loops, we could put an equation in, let me go to edit mode here. Okay, so in this container here, we could say in our looping, we could create an equation that says continue looping until some criteria is met. And in our case, we're going to say Q4, which is our target point in the cycle. It's going to say keep looping until the flow at Q4 is equal to the target flow minus some tolerance. So let's go in there. So we have a tolerance here of 1 liter per second, and it's going to say keep looping until the flow here at Q4 is pretty close to the target flow with some leeway, right? Because we don't want to force try to be exact. We're never going to get exact. And so the way that we change the makeup flow that comes into the system is based on the number of loops. Okay, now this is not using any kind of fancy root zero solver, although we could definitely do that and it would probably solve the solution faster. What we're doing here is just very crude, actually, and the reason I want to show it this way is because it's really not that expensive computationally, and it gets us the answer pretty quick with not that many loops. But I'm just saying that you could actually implement a numerical solver that would require less loops than what we are requiring. All I'm doing here is I'm saying I'm going to start with an assumption that the makeup flow coming in is very small at the beginning of our loops. Now remember, the looping container, it does this every time step, right? So on each time step, it's going to start its looping, and everything in here will continually update until our condition is met, which is that Q4 is about equal to the target flow, right, minus the tolerance. Okay, so the important equation here is in the makeup right here. So this makeup says, all right, what I want you to do is I want you to say, look at the loop count. That's how many loops this container has run. Multiply that by 1 liter per second. So that means on the first loop, the makeup flow is 1 liter per second, a very small amount. And it's going to most likely mean that it's not enough makeup water, right? So it'll say, well, our Q4 is not high enough to meet our target. So then it will loop again, and it will be 2. And that'll make it 2 liters per second. And then we just work our way up slowly until, not slowly, but on each increment until we have enough makeup water that meets the criteria. So then we run this, and you can see that our makeup water is looking like that, and Q4 looks like that, and we get something that looks like this. So our target is there, and our makeup water is here. And we could make some adjustments here on our tolerance. We're working with very small flows here, as you can see. So in some cases, 10% is the tolerance. So it's a pretty high number. So what we could do is we could increase the number of loops that it can do and decrease our tolerance. But in most cases, your flows will be much greater than 10 to 40 liters per second. Somebody said, in this case, the multiplier in liters per day should be equal to the tolerance, shouldn't it? That's a good point. My tolerance is 1 liters per second. I mean, I am incrementing it by 1 liter per second each time, but I don't know. I would say that you're probably right. Yeah, it probably wouldn't make sense to have that a different number. We could probably just put the variable tolerance in there, and that would be fine. But I guess my point is that we could make that tolerance number, whatever that is, smaller than 1. Yeah, in this case, some smaller fraction than whatever this this flow is, something less than 10%, obviously, and that's what I have. And the other thing we could do is track the number of loops that we're calculating just by putting an expression in here that looks at the loop count. Sometimes that's important to just see that and plot it over time. So this is the number of loops that we're calculating. Most of the time, we don't need any makeup water, but when we do, then that's how many loops it's calculated, 14 in that case. Okay, so it's another way to solve it. All right, so knowing all of this, let me go to a realistic model. This was a model that was created in a training class. So a lot of times in the training courses that we give, we give a 2-day basic training, and then on the 3rd day, we help build a model for the customer, whatever they're working on. We just kind of construct it from the ground up, design the model, and pretty much create a prototype during the day for their system. And then it provides them a springboard for continuing on with their modeling after the training. So this was developed for that purpose, and I've stripped it down and made it quite simple, removed all the names and so forth. But if we look into our, what's right here is called Flow Solver, if we go in there, that's the same kind of thing we were just looking at, a looping container that it iterates until some makeup water is being calculated and the condition is met. And here's the model. This is very similar to the picture that you saw on our website, and it's using what are called custom icon images. These are all just regular elements. This is a sum element. This is an expression. This is a pool element, right? So what I mean by that is if I make a copy and I go here to appearance and I change it to the default symbol, oops. Sometimes you'll see when you use a custom icon, you've changed the size of it, so the proportions of the icon are no longer square. So if you hit reset size, it will change it, right? So that's the correct size. Anyway, this is a pool element. All I did was just change the icon to look like this little treatment plant thing. Okay, this model is a simulation of a mill at a mine. And what we have is fresh water being delivered into the system here. And we have an old mine pit here with some water in it that they're trying to remove. And that was a big part of the reason, that was the purpose of this particular model, was to see how long it takes to remove the water from this pit and what to do with that water that needs to be treated and so forth. There was also some other dewatering going on in the mine elsewhere. And so those flows come in here and are forced into this thickener along with some makeup water that comes into a tank and then is discharged into here. Water is then removed from there into the tailings facility here. This is a barge pump. Some of that water goes to the tailings, some of it goes back into the system. So you can see there's a flow loop here, and there's another flow loop here. The mill here is where the water is actually needed for production, and so it's really important that you have the right amount of water flowing in this cycle here, which means it's very important that the water in the thickener is held constant, right? You don't want to run out of water here. And this is a storage element in the simulation. And so are some other points. Obviously, these tanks are storage elements. The pit is a storage. The sump is a storage. And anyway, so there's a flow loop here. And we had to put in a previous value element here in order to break the delay that's happening in this flow loop here. The reason for that is because our residence time in, for example, this thickener is very small. It's less than 1 day. But our time step, if we go here, you can see our time step is 1 day. Okay, so this is a similar case that I was showing you before, where because of our small residence time and because of the fact that we have flow loops like this, it's important that we do not delay for an entire day. So that's why there's a previous value element here to help us with this loop. You can also see that we have some arrows going opposite directions here and here, and this is because the state of a particular point in the system, let's say for example at the sump, is controlling how much water is coming out of this other node up here. So what we do in this model is we say, okay, as the sump begins to draw down, water in the sump, as it draws down, then we need to increase the discharge from this tank here into the thickener. Then the thickener just overflows into the sump. But that's why we have arrows going this way. And if I go into the sump, you can see what we're doing here is we're saying how full, and there are multiple ways to do this. We could look at the water level in it, but I'm just using a percentage. I'm just saying how much water is currently in the sump as compared to what its capacity is. And then we come over here and we say there's a lookup table that says based on how full the sump is, then we're going to ask for up to a capacity of flow from the tank upstream. So that's why a downstream point is talking to an upstream point. Okay, and then because of how small this this is called a freshwater pond, and I've just used a picture of a tank, but they're actually little ponds. They're actually quite small though in relation to the flows. And in this case here, I did the looping solver. So if we go in, I have what's called well supply, and so this is what we need for supply from the makeup water wells to come into the freshwater pond. And as you can see, I'm using loop count, and I'm multiplying it by some incremental flow, starting with 0 because I have -1 right there, loop count -1. So we start in the first loop with 0 flow, and then what I do is I have criteria that continues looping until this is up high enough that we have met the flows that are needed in this pond. So if I go up to the looping criteria, then we have here, it says, what I'm doing here is I'm just saying keep looping until the inflow into the pond is greater than whatever we're requesting to be removed from that pond. And yeah, this might be overkill in this particular case, but I'm just wanting to show you how I'm using a solver or a looping container to solve for this flow. Okay, so if we run this model, then we look at, for example, the flow going through the mill, and these are the flows going through there on a daily basis. The amount of water in the pit, well, I have all these results here. Let's see. No, I don't. I don't have a flow model or a plot of the pit water. So there's the pit water as it's being drawn down over time. Okay, so this this all worked pretty well, and we were able to maintain a fairly large, relatively large time step and still calculate everything without having major oscillations or problems. Another important point that was found in this model is that in reality, the way that the thickener works is there's a rim all the way around the clarifier, right, or a weir, and water flows over this weir around the edges. And so the way that we actually started simulating this or building this model was to simulate a weir at the clarifier there and say that, okay, based on the depth of water over this weir, we're going to calculate a flow, and that's all fine. It works great. The problem is it doesn't work great on a one-day time step because you have these little fluctuations that are occurring in real time, and the dynamics of it just require that you have very small time steps because what we're dealing with here are daily average flows, and so your equation breaks down. The solution is that you start to have major oscillations because just a small fluctuation in that water level, right? The model's very sensitive to those fluctuations. And so what we would have to do is make the time step quite small. And what we were doing is probably around 5-minute time steps and for it to work. And that was because the residence time in this clarifier was about that. It was about it was something less than an hour, I remember. And so having very small time steps worked just fine with the weir equation at the clarifier. But another approach to this is just to say, no, you know what, it's just a mass balance we're working with here. Therefore, we should just put in a capacity at the point of the weir in this clarifier, and then just say whatever flows over that is overflow, and that's what is discharged from this point. However, when you're dealing with an overflow output of a reservoir or pool element, this thing right here, the overflow, that is not a state variable, and that will cause you to have a recursive loop in a flow cycle like this if you don't have a previous value. And that's a case you might have encountered if you're building these kind of models, where as soon as you refer to the overflow, you'll see that you get a recursive loop error in your flow system, and that's because that output overflow is not a state variable like the pool element is, or the pool amount is, which is this output symbol that has a black line there. Any output that has a black line next to it is referring to a state variable, and when you refer to those kinds of outputs in a loop like this, you will not have a recursive loop error in your model. But as soon as you refer to one that is otherwise, then you will get a recursive loop error, and you'll have to put in a previous value, and that's why I have this here. But it doesn't matter, right? Because I'm looping the container, and so I don't get the delay, so it works out. Okay, so we're getting close to being out of time, and I realize that this is a bit of a complex model, but I will make this model available as soon as I post the recording of this video on our website, so you can have access to that. And just to review, that you can get to our webinar archive to look at old videos just by clicking here on the Help Center, and then just go to Webinar Archive. Okay, so let me just say a few notes about these custom icons, since we're kind of out of time, and it doesn't have anything to do with the subject of this webinar, but I did see that a lot of people were interested. So I have a PowerPoint file. If I open that, this is where I build these icons, and I just have a whole bunch that I've been working with over time, and I've just drawn them in PowerPoint actually. So let me zoom in here. So here's my sump icon, and it's right now it's grouped. So if I ungroup it, then you'll see these are the individual components. It's not really that complicated, but it's just you can see I have shadows on there, and in GoldSim 12 it it works with all of this kind of stuff, shadows and all that very nicely. But that's essentially the sump, right? It's just all those little parts and pieces. So then all you have to do is just right-click on all of the parts that you want and click Save As Picture. In my case, I grouped it first just so it's easy to manage inside the PowerPoint. But then I just went over here and I said Save As Picture, and then this is the important part right here. Make sure that you change it to EMF. Hang on, let me go to downloads. Okay, so you don't want to save it as PNG. You want to save it as EMF, and this is the EMF Plus type that is able to be used in GoldSim and rendered nicely in GoldSim. So as soon as you save it as that, that's the thing that you can use inside of GoldSim. So what we've done on our library, if I go back to the library, whoops, library, you'll see we have an image library here, and we have element icons, and then we have them categorized here, environmental systems modeling, and here's the sump. All you have to do is just click on the link here. I think you can click on the image too. Anyway, you can see it downloads this EMF. Then you just simply go over to your model and you say, I don't know, I guess I want this thing to be, I don't know, I'll have this be my sump here. So you just right-click on the icon and go here to Appearance, and then select User Defined Symbol and go to Downloads, and there's the sump. I actually downloaded it twice accidentally. And then right here is the important point. It's asking me if it's saying that the size, the dimensions, the height and width of this custom icon are different than the height and width of the default icon. And it's asking me if I want to force the new icon to be within the bounds of this old one. And I'm going to say no every time, because I just want to maintain exactly the ratio, the height width ratio of my custom icon. I already created it. It's exactly the way I want it, right? I don't want to mess with it, so I'm going to say no every time. But it causes it to come in at the size that I created it in PowerPoint, which is different than the size of all these other elements. And that's fine. And you know what? I could have spent more time inside of PowerPoint making them exactly, the right size that they need to be when they come in here, but it's just too much work. So all you have to do really is just make it use the same size as command. So just highlight another element and then just come up here to the space across button and then go to the little drop list here and then choose same size. And oh yeah, this is not actually what we're going to want. I just went to undo here. You have to start with something that is of a similar type, and right now this is the only custom icon we have in here. So I'm just reducing the size. And by the way, on the appearance here, if you go to the locking tab, you'll see that the aspect ratio is locked. I think this is filled in because the ID is not locked, but the image is locked. Anyway, don't worry about it. As soon as I do this, you can see that it's maintaining the ratio, but it is rescaling. Okay, so now when I add another icon, now I can make everything the same size as this one here. Okay, so let's say I go over here to this node here, and I go to Appearance, and I make this one look like the well. Then all I need to do is highlight my other custom icon, and the same size should get me exactly what I want. Yeah. So once you've created the first one, then it's just a matter of making it the same size as that each time you add the next. So that's how I added all of these in there. All right, so that is the end of our presentation.